Hi, and welcome back to the Save It for Parts channel. Today I'm following up on a prior video where I assembled the RASCube LB, this CubeSat analog from Robinson Aerospace in Australia. They sent me this a while back, and it's basically a fully functional model of a minimum size satellite, a 1U CubeSat. So this has all of the same electronics that a real satellite would have. It has an onboard computer, sensors, telemetry radio, GPS. It's not designed to fly in space, but it is a cool model that kids can build at schools that you can put together for STEM classes and learn about space travel, or learn about satellite technology, learn about the steps that go into building and potentially flying a satellite, although these again are not designed to go into space. So to follow up, we have the Robinson V2, the RASCube V2, and this is an upgraded version of their educational CubeSat kit, and a version of this has actually flown in space. So right here is something that is probably the closest I've ever had my hands on to space-proven hardware. So the Robinson V2 CubeSat actually flew on Transporter 14 on a SpaceX mission, and it was kind of a rideshare on a rideshare. It went on the Nix capsule, which was a human spaceflight demonstrator that had a bunch of different CubeSats on board. And that capsule was supposed to orbit for a while, come back to Earth, re-enter, and return the CubeSats, including Robinson's V2 test model. Unfortunately, there were some parachute issues and it crashed. So they didn't get their test item back, but they were able to test it in space, and they were able to prove that the Robinson V2 can operate in orbit, which is pretty cool. I cannot afford to send this to space. People always ask me, what would it take to actually get this into space? It would take $50,000. Even something as small and lightweight as this, yeah, it basically costs the same as a mid-sized car to get something like this into orbit. So I will not be doing that anytime soon. Maybe when I have millions of subscribers, I can afford that, but it's not something the average YouTuber can do. So in the meantime, we are going to assemble it, like I said, and I'm going to do some tests on the ground because I do have a vacuum chamber. I do have some things I can do to this that will get close to some of the things it would encounter in space, if not identical. So we'll get to that later in the video. First off, let's see what's in the V2 kit. And we looked at this very briefly in the other video with the LB. They sent me both at the same time. We've got an instruction manual. We have this assembly mat. This is really nice. When I assemble stuff just on my desk here, the little screws tend to run everywhere, things roll around, things get lost. Yeah, they thought this out. When they're giving this to students to assemble, students will lose small pieces left and right. So this is a great idea. And underneath that, we have the framework structure of the CubeSat, and the V2 here actually uses a metal structure, so that's pretty cool. The first one was just plastic, so this one has metal side rails. Just like the LB, we have a couple modules here. We have the EPS, or power module. We have the OBC, the onboard computer, and this one is also an upgrade from the LB because it has a little camera. So the first one that I looked at from Robinson did not have a camera. We also have a serial radio module over here. That's basically our ground station. That is going to connect to my computer and act as the radio link to the satellite. And we have some more parts down the bottom of the case here. We have a sensor board, a telemetry board, a prototyping module, so I could add my own sensors and devices to this if I wanted. The LB also came with that, at least the one they sent me. The system has an Arduino microcontroller for the brain, so you can add kind of standard Arduino accessories to this, and that's a great idea for students if they want to develop some kind of remote sensing or human interface or something. That's really cool. It makes this whole thing more expandable. We also have some solar panels, another upgrade from the LB. So we have solar panel side modules. We have this other custom side panel that exposes the camera and some of the interfaces. We have a custom top panel with the GPS antenna and then a telemetry antenna and some radio interfaces on the bottom. Yeah, definitely a step up from the LB. It's a little bit more expensive, but it is nicer. And again, this is a device that has flown in space. It did have a little bit of modification from the base kit here. They did some redundant electronics, so I think maybe they added another OBC board. They maybe added a few more things to make sure it would work in space in the radiation environment and whatnot. But basically everything you see here could theoretically go into orbit, so I think that's pretty cool. In addition to the satellite kit, they also sent me this test bench V2.0. So this is kind of cool. This is like a, it's something called a flat sat. So you can take your satellite parts and lay them out on this test bench. And you basically have all the pinouts exposed, you have the bus exposed here, and you can test individual modules. I'm going to start assembling the electronics as if we were putting them into the satellite, but instead of assembling the metal structure, the fuselage first, I'm actually going to put things together into the flat pack here. All right, there is our flat sat. Yeah, it took almost no time to assemble that. And I think we can now power this up and actually look at the telemetry. We don't have to do the full assembly process. So this definitely gets you started with the hardware much faster than otherwise. I'm still not having any luck with this thing. The LB makes a startup noise when it initializes, when it boots, and this one is not making any noises. So I think there's something going on here. I'm just going to put aside the test bench for now, and I'm going to assemble the satellite as intended. Maybe we'll come back to the test bench later. Maybe we can hook that up on top of the stack and use it for the evaluation boards or something. Before we get to the main assembly, I wanted to point out how nice these circuit boards are. They're very well laid out. They've got a lot of good labels on everything. So our power board here on the bottom not only has the logo and the website, we've also got a little slogan up here. And then we've got some pinouts if you want to take an oscilloscope and look at the inner workings of this. You can look at the clock, at the TX pins, all that stuff. On the top we have our main stack, our bus connectors, and those are all labeled. This is the power board, so we have a control circuit, we've got a charging circuit, a switching circuit, regulators, USB, solar, everything is labeled. So if you're teaching students about circuit boards, if you are doing any kind of circuit board work, you can get a really quick look at what's on here. And then we have all these indicator lights for 3 volt, 5 volt. You can stick your multimeter on here and really quickly trace out where everything goes and what your reference values are. On the computer board, the brain of the operations, we've got we've got an Arduino chip, we've got a couple other chips, we've got programming USB, logic level converter. That's something I'll be working on in a future video. Quite a few more indicator lights. We have our camera over here, again our bus edge connector, and we have a breakout over here. So if you want to add even more than the prototyping board lets you do, you could put another header on here and you could put even more stuff on this. We have the serial number on here so we know what to use to talk to this. We have some more Arduino breakouts, and then we even have even more breakouts up here, STM debug. So there are so many ways to interface with this thing. Moving up the stack, the sensor board has a GPS module. We actually have a little battery here. I don't know if that's for a real-time clock or what that is exactly, but there is a tiny little watch battery. We have a barometer sensor, our magnetometer, we have the IMU, or inertial measurement unit, and on the back here it actually tells you what each of the chips are. So the IMU is an LSM 60SO, the barometer is this MS5607, the magnetometer is an LIS 2MDL, and the GPS is a ATGM 332D. So if you want to look up spec sheets on those, it tells you exactly what chips it's using. And you don't have to get the microscope out and try to figure it out for yourself. Finally, for my assembly, the top board is going to be the telemetry one. This is similar to the LB version where we have an RF transceiver, a little serial radio, our antenna connector. If we were going to put on the prototyping board, that would be the top of the stack probably, but I am not going to do that just yet. We might look at the prototyping board later, but for now I'm just assembling the 4 main boards that came with it. So let's go ahead and get the fuselage assembled, the parts all together. Let's build our satellite. Robinson has very helpfully included 2 tools, so if you're working in a team of multiple students, there are tools to go around. Another nice, thoughtful feature. I'm just going to go through this, follow the manual. The manual is super straightforward, just like the LB. Everything makes a lot of sense here. I have actually read through this one first, so hopefully I don't skip any steps or get anything backwards. And yeah, we'll just put some music on and get this put together. And I already started to screw that up. I just said that they gave me this nice rubber mat for assembly, and then I forgot to use it. So let's use it. All right, so there is our Robinson RASCube V2. I immediately noticed this is much heavier than the LB, which makes sense because the LB is just 3D printed plastic. The V2 is a metal structure. It has all these extra panels on the outside. It has solar panels, where the LB was just an open frame. There's an extra circuit board in here. This one just has AA batteries, where the V2 actually has rechargeable batteries, so there's quite a bit more in here. So fully assembled, the V2 is about 706 grams, whereas the LB is less than half that. It's only 333 grams. Yeah, the V2 here definitely feels more like a real satellite, and it should, because it is, again, this is space-rated hardware. This is something that has gone into space. I did have a couple issues while putting it together. I screwed up. I had to go back and redo some of the orientation of the top and bottom plates. It really does matter of the orientation. It is not a perfectly symmetrical cube. So yeah, again, I should have looked more closely at the manual, and the manual does say, just, you know, pay attention, go slow. I could not get one of these fasteners in. It was kind of out of alignment. I tried taking the fasteners off. I tried shifting things around again. Yeah, it was really hard to get that last screw in, and I think it ended up kind of, the interior nut or insert is now spinning, so I can't get that last one in. It doesn't matter too much. There's 3 out of 4. Yeah, it bugs me a little bit, but I think from a structural standpoint, it doesn't necessarily need that screw. Maybe I put a little too much pressure on that when I was screwing it in. I noticed some of the screws, you need to really push them, especially going into the side rails. Other ones go in pretty easily, so it's kind of various amounts of force to put different things in place. So let's fire this thing up again and see if it works. We are going to open up Mission Control again, select that serial radio, select the serial number here, open this up, and we're going to pull out the RBF pin. And this time it sounds like it booted. It actually made its happy little noise. We have a blue light, and on the telemetry panel, we have data. So yeah, there is data coming in. We've got all the stuff from the LB and more. We have yeah, charging data, we have battery draw data, we have the sensor data, orientation, acceleration. We don't have a GPS signal yet. Once that kicks in, I might have to blur that out so I don't dox myself here. But yeah, we are getting telemetry from the satellite. And if I pick the thing up and start moving it around here, yeah, we can already see the gyroscope and orientation, and the acceleration sensors are all responding. It says we have a camera connected. We are green on all systems here, basically. And we're getting solar power in, so we've got solar voltage from the 3 different panels. If I move this around, if I face a different panel towards the sun, it's really obvious right away that one is getting more sun than the others. That's pretty cool. So yeah, we can kind of tell orientation relative to the sun with that, at least in one axis or 2 axes here. Let's try out the camera. On the dashboard here, we have a camera button. So if I click that, all right, we're getting camera data. It's really slow. It looks like SSTV almost, but the camera is showing my camcorder. That's pretty cool. Yeah, it's really interesting how it loads kind of chunk by chunk there. I'm going to go ahead and download that and see what that looks like. It's a pretty low resolution image, and that makes sense if you're trying to send this over serial radio. There's not a lot of bandwidth to work with, so yeah, this is pretty small. It's 320 by 180 pixels. All right, I think we have to get a cat picture with this thing. That is a requirement. That is a mission requirement. So let's see if we can get a picture of Fluff. So for my first space-like test, I am going to throw the RASCube V2 into my vacuum chamber that I picked up from Axeman Surplus. And I have a different vacuum pump I'm going to try than last time. If you watched my video on the MySat, you may remember this guy. We tested the space-rated Prusa filament with this thing, and I used kind of an older vacuum pump for that one. I've also got this vacuum pump, which I think I figured out. I found the manual for it, and I think I have the settings right. I think this one will go a little bit lower, but both of these vacuum pumps were free. They were both basically dumpster dived from a science lab, so I don't know how well it'll work, and I don't have a great gasket for the chamber here. I've just been using Teflon tape, so we'll see how it goes. Just like last time, I've got a GoPro running inside the vacuum tank, so we can hopefully see what's happening with the pressure gauge. Okay, this thing is making a distinct burning oil smell. That's probably a feature, right? That's definitely just condensation coming out of there, not smoke, right? I think it's time to put on the safety glasses in case that thing explodes. I did find it for free, so. It says it was last serviced in 2023 with the oil changed, but I don't know if it's been run since 2023, so who knows. Either way, this sticker will make everything safer, and you can buy these from my merch shop if you want to make your project safer. All right, I don't know if this is at full vacuum yet, but I'm going to turn this off for a moment. Just listen for any leaks around my chamber. I do hear a very, very slight leak right over here. This worked better than the last time I used this with the other vacuum pump. We got down to about negative 14.1 psi. And since we're starting above sea level, I'm about 700 feet above sea level, my local pressure is something like 14.3. So we're getting a difference of about 0.2 psi. That's essentially the pressure inside the vacuum chamber at this point is 0.2 psi. Which is, yeah, that's better than last time. Last time we had about 1.3 psi. Now for this test, I did not have the satellite inside the vacuum chamber. I'm just testing the pressure to see how this pump works. I threw a balloon in there to just illustrate the difference in ambient pressure versus vacuum. This balloon was deflated when I started, and it blew up just from the few molecules of air that were inside of it relative to the low pressure inside the tank. So that's kind of a fun illustration. So I think we're ready to send the RASCube V2 into space, or again, as close as I can get here in my garage. So we've got the CubeSat positioned inside the vacuum chamber, propped up on a tripod. I have a little camera there that Bill Frovick gave me that's looking at the CubeSat. Thank you again, Bill. That camera is coming in handy. And then we have the GoPro again that's going to watch the pressure gauge and hopefully also the satellite. I'm going to have to position things here so nothing collides. I also have the laptop here running the ground station radio so we can watch the pressure and altitude in real time on the telemetry. Well, we're still getting data through the metal walls of the vacuum chamber, so that's good. Vacuuming the vacuum chamber. Wow, you can really see the pressure respond to that. So I'm going to request an image here. And it's still sending images. We can see both cameras. We're at a simulated altitude of 20,000 meters. And the gyroscope sensor is actually picking up some vibration from the pump system. I know it's noisy over here with the pump, but yeah, I've got this little pressure gauge inlet here. So this is basically an inverted pressure gauge built through the top of the chamber, and then I've just got a ring of rubber cut out to seal that. So it basically suctions itself down onto the rubber. The outside air is going into the gauge here, so the gauge inside the tank is reading outside pressure, and that will basically tell me kind of the PSI of the outside air. All right, that has definitely leveled off, if not started to go back up on the pressure. So yeah, we're kind of up and down on pressure and altitude here a little bit. It looks like the best vacuum I can get is around 11 HPA, or I think 11 millibars. I'm going to grab one more image from the CubeSat at the minimum pressure here. So I am going to turn off the pump. And yeah, we immediately see the effects of leaks in the system, pressure going back up, and I'm going to go ahead and open the dump valve here, and we'll send it down. Maybe I don't want to send it down too fast, but we will let some of the pressure out. So let's get this opened up and look at the GoPro footage, which probably won't look like anything because it's just kind of a satellite sitting there, but we'll be able to watch the needle go down on the analog pressure valve. Boy, the GoPro got really hot in there. I think it's hard to cool things down in a vacuum because there's no air movement around it. For the next test on the RASCube V2, I threw it in the chest freezer, and we'll leave it in there until the temperature stabilizes and just see how it handles freezing temperatures. I am still getting telemetry even from inside the chest freezer all the way up here to the office, so the transmitter on that RASCube V2 is pretty decent. So we got this down to about negative 18°C, and everything is still working. We can still get pictures from inside the freezer. The freezer itself is a little bit colder, but I think possibly the RASCube keeps itself warmer because it has some electronics running, and I never really saw it get colder than that on the temperature sensor. So after a few hours, I took it out and let it warm back up. Alrighty, we have brought the RASCube V2 out to Sandland to put it on a rocket. Now, obviously, this isn't a real rocket. This is a free grain silo with some trash duct tape to it, but it's the closest thing I have to a big rocket. So I think it's appropriate to stick the RASCube up in the nose cone, and then it's up kind of high, and we can drive around the area and do some range tests on the little radio. Is this silly? Yes, it's absolutely silly, but this is the kind of thing that would really excite my inner child, and if I had an inner adult, they'd be excited too. I'm a little concerned now. I can't get it to make the boot up sound. Yeah, have I damaged this by putting it through the vacuum chamber and or the freezer? Did I damage it by taking it out of the freezer? I have let this sit next to the dehumidifier after taking it out of the freezer so there wouldn't be any condensation inside. The green lights are all on, but it doesn't seem to be booting up the onboard computer, so we may have to do a little more debugging first. Yeah, we are still not booting, so I've done something wrong to it. So I can confirm that the test bench works. We just had to move this wire to the correct location. We have the satellite laid out on the test bench again in flat sat format, and it is powered up. Everything seems to be working. We are connected to the ground station radio, and it turned out that the ribbon cable down here was actually plugged in like slightly one off. It's got some extra space on either side of the plug, so it's possible to plug it in, basically miss some of the sockets on these connectors. And this is a great way to poke around with a multimeter or an oscilloscope and get an idea of what's going on within the satellite bus on the system here. You can kind of get to all the parts, you can get to all the test pinouts. When the satellite is flat in front of you, you can't really access a lot of these headers or test pins when it's assembled. So yeah, this is just a great way to diagnose and check on the electronics, learn more about the electronics, prototype things, change things if you wanted to add additional modules. So the test bench is really convenient for that, and that is a nice, thoughtful addition to the educational mission of this satellite, because that's something that is really geared towards students, really geared towards educators, experimenters, and people who want to learn more about this. All right, I think we may have gotten this thing to boot reliably again. Let's go ahead and test that. Okay, yes, everything seems to be working again. We've got telemetry. The satellite is functional again. So I think we've maybe solved that intermittent failure to boot issue that I was having. And all I really did was leave this out in the sun for a while. I set it outside. I let it basically bake in the sun, just kind of as the idea that if for some reason between me putting it through the vacuum chamber several times, putting it in the freezer, letting it dry out from the freezer, which I did overnight next to a dehumidifier, so I don't think it got any condensation in there, but then going into the car, which doesn't have AC on a hot day, driving out to Sandland for an hour, this thing had gone through quite a few extremes. It had gone basically pressure up and down, temperature up and down, humidity changing from inside the house by the dehumidifier, outside in like 80% humidity air in the summer in Minnesota. So my suspicion was that some moisture got driven in somewhere, maybe under a chip or under a connector, and it was just kind of very slightly shorting something out. So I thought if I set it out in the sun, if I let it sit there in the sun all day and kind of bake, maybe that will bake out any latent moisture. And that seems to have worked, because now it is booting consistently. This would be a great time to talk about what makes a real flight-worthy satellite and how Robinson did some additional things to send this into space, because if it has a boot issue like that when it's in space, well, you can't go up there and power cycle it very easily. So oftentimes you'll put on a redundant processor, so you put on a second brain board that can take over if the first brain board fails for some reason, or you'll have some kind of a watchdog circuit or a babysitter circuit which checks to see, is the satellite operating, is everything working, has it booted up correctly, and then can just trigger a reset if something's wrong. Maybe there's a timer in there to delay and say, hey, if it hasn't booted up, let's try rebooting it every 10 minutes or so. And on orbit, if the satellite is flying around the Earth, it's going through a lot of hot-cold cycles, it's going through direct sunlight, shadow. The temperatures are swinging quite a bit more than they do here on Earth, quite a bit more than I can get to just going from a hot car to the freezer or vice versa. So it's good to have something like a watchdog circuit on your satellite in case it has an issue with booting up, in case it loses power and needs to be restarted. And that is something that Robinson did when they sent the version of the V2 on that NIX mission, on that Falcon transporter mission. They had some additional redundant circuits. Honestly, I think building a watchdog circuit could be a really cool educational experience and a very real-world application of CubeSat technology. Now, I have some extra Arduino parts and modules. They gave me the prototyping board. I don't actually have time to put something like that together, but it's kind of on my radar now. It's kind of on my potential to-do list is, can I put a second Arduino on the prototyping board? Can I have some kind of feedback from the main board to reboot it if necessary? That could be a fun follow-up. I don't know when or if I will actually get around to that, but the wheels are definitely turning, and I think that would be a great way for a school to integrate this into a curriculum. How do you keep that satellite operating under extreme conditions? And yeah, it was definitely a little stressful for me when this wasn't booting up, but I learned a little bit, and I got some ideas about how to prevent something like that in the future. So I'm going to call that a win. I'm going to call that an educational experience. Now I just need to put this thing back together into CubeSat form. So big thank you again to Robinson Aerospace for trusting me with their fancy V2 CubeSat, as well as the LB, which I did in a prior video. I've got that in the case behind me. So yeah, they saw what I did to some other CubeSat models. They saw the abuse that I put them through of temperature and pressure changes, and they were willing to send me their own to see what I would do with that. And I did worry for a minute that I had damaged it, but it is everything was fine. We got it working again. So yeah, I would say this is a pretty cool CubeSat that, again, is the closest thing that I've ever held in my hands to something that could go into space. So if you're a school or a college or an educator, if you're somebody who's interested in one of these, I will put links down below in the description. They are budgeted a little bit more for schools. They are not necessarily budgeted for the average student, but if you have a STEM program, if you have an aerospace program, I would highly recommend this because they make these really well thought out. They do a lot of extra, very thoughtful things designed for students, aimed at teachers, that I think are really cool. The test bench, all the extra parts, the assembly mat, the very clear instructions. They have guides online, they have teacher resources online, they have lesson plans. So yeah, I'm not a teacher myself, but if I were, yeah, I would definitely use this in a class because this thing's fun. We're going to wrap this video up, but if anyone has suggestions for things we could do with the Robinson V2 or the LB, let me know down in the comments. I do have some ideas involving weather balloons. That might have to wait a little bit. Helium is very expensive, so we'll see what happens with that. If you have other ideas in the meantime for modules I could build or experiments I could run, yeah, please do let me know. Finally, thank you to everyone out there for watching, and we'll see you next time.